So as of now we have done talking about fire and everything related to fire. And you still remember chapter 6 is talking about two things, fire and explosion. So we have talked about fire and now we're going to talk about explosion, and we're going to start with what we have already seen before, or what's the definition of an explosion. Explosion, as we explained earlier, is a quick or sudden release of energy that happen in a very short period of time and result in what we call a pressure wave or shock wave. And this shock wave or pressure wave or the blast is the main reason for the damage that you see. That's why when there's an explosion, one major characteristics of the explosion is that you will see a huge damage in large area. You will not see the smoke and the flames that you have seen it before in the fire. In the explosion, you will see no. You will see, for example, cracking in windows or damaging for buildings, or you will see, for example, fragments, pieces of material that's splitting everywhere. And there are mainly two types of explosion. There is the first type is what we call the deflagration, and the second type is what we call the detonation. In the deflagration, the reaction wave speed will be less than the speed of the sound, which means that the pressure wave is moving in a speed less than the speed of the sound. In the detonation, reaction wave speed, or the speed of the pressure wave, is moving in a speed greater than the speed of the sound. And if you still remember, the speed of the sound is 344 meters per second approximately. And normally you have to keep in mind, as a rule of thumb, that most of the flammable material, such as hydrogen, such as benzene, toluene, hydrocarbons in general, they will give you what we call the deflagration type. Where the deflagration type, where the wave of the speed wave of the reaction, or the front speed of the wave, will be less than the speed of the sound. In the case of the detonation, the speed or the wave of speed will be greater than the speed of the sound. So most of the flammable material will give you the first type, which is the deflagration type. In this slide, we're going to use this scheme on your left to explain what's the difference between the two phenomena, which is the deflagration and the detonation. First of all, let's identify certain things. The gray area is what we call, let me just use, for example, yellow. The gray area is what we call the reacted gases in the two cases. The white area is what we call the unreacted gas. I'm going to give it the blue color. You see it here, you don't see it here in the case of the detonation. And the purple part is what we call the pressure wave, which is this part. This is the pressure wave. And the green part is what we call the front or flame or reaction front, which means that here is the zone or the origin of the reaction or the explosion, and the green part is what we call the front or the reaction front. Now, if the reaction front is moving in a speed less than the speed of the sound, which means that the pressure waves will move much faster, and there will be always a distance or gap between the pressure wave and the front of the reaction. So if there is a gap between the front of the reaction and the pressure wave, where the pressure wave is moving in the speed of the sound or close to the speed of the sound, and the front of the reaction is moving in a speed less than the speed of the sound, this means that there is a gap between the front of the reaction and the pressure wave, and this will cause, or this will lead to, what we call the deflagration. Now, if the front of the reaction is moving at the same speed or higher speed than the speed of the sound, which means that it's following closely to the what we call the pressure wave, and the pressure wave is slightly ahead of the reaction front, this means that we have what we call detonation phenomena or detonation type of explosion. And normally, as I explained earlier, the deflagration type will be resulted from all the flammable material in general, and the detonation will be very common, or will be very common in the case of what we call the TNT, اللي هو famous explosive material, and one of the main fundamental اللي هو الديناميت. And one of the main fundamentals for the detonation, that the detonation reaction or the detonation explosion will be localized. So all the energy will be focused in one point. Meanwhile, the deflagration energy will be splitted or distributed among large area. Meanwhile, the detonation, the energy or the amount of energy will be transferred or will be focused in one single point. That's why انت بتستعمل دائما الديناميت or TNT when you do, for example, اللي هو في mining, or for example when they open roads في mountains, they use the dynamite or the TNT to make an explosion, a localized explosion that is very strong, and that can able to crack, for example, rocks, and all the energy will be focused or concentrated in one specific area. So TNT will normally give you what we call detonation, and flammable material will give you what we call the deflagration, where the deflagration is that the front of the reaction is moving in a speed less than the speed of the sound. Therefore, there will be a gap between the pressure wave and the front of the reaction. Meanwhile, in the case of the detonation, the pressure wave is moving slightly ahead of the what we call the front of the reaction, and as a result, the front of the reaction is moving in a speed greater than the speed of the sound, and the two speed will be very close to each other, and as a result, we call this a detonation. Another interpretation for the detonation and deflagration, as we mentioned, in the case of the detonation, the difference or the area or the distance between the reaction front and the pressure wave is very small, is very limited. This means that you have what we call the detonation, and as a result, you get the maximum value of the pressure exactly at the specific point. That's why we said that the maximum amount of energy will be focused in one point, and this is what we call the shock front, where you get the peak pressure at a specific point. Meanwhile, the deflagration, there is a gap between the front of the reaction and the pressure wave, and you will see that from the shape of the pressure in terms of or with respect to distance, the maximum pressure or the peak over pressure, and we're going to identify what do you mean by the peak over pressure in the next few slides, or the maximum pressure will be recorded over a range of distance. So it will cover range of distance from here, for example, to here. This distance will all covered by what we call the maximum amount of pressure that can be achieved. Meanwhile, in the case of the detonation, when you look at the pressure measurement with respect to distance, you will see that the maximum pressure will take place at a specific point, and this will give you what we call the maximum pressure or the peak over pressure at specific point. Meanwhile, the deflagration will cover like large area or large distance or large region of distance. Another explanation or interpretation for the detonation and the deflagration, as I mentioned, the detonation will cause what we call the localized damage, and there will be lots of pieces in the case of what we call the detonation. In the case of deflagration, the damage will be split over large area, and you will see few pieces. Detonation will come normally from what we call TNT or dynamite. Deflagration will come from flammable material. One more thing is the wall thinning or the non-wall thinning. Wall thinning is referring to what we call or what we call the weakening of this construction points or the construction for buildings around the area. So if you see any weakening for building, this is a result from, for example, deflagration. And if there is no wall thinning, this is an example of what we call detonation. Another way to classify explosion is what we call the confined explosion and the non-confined or unconfined explosion. The confined explosion is when the explosion took place in a closed area or closed space or specific system or unit or equipment. This is what we call confined explosion, and in that case, most of the thermodynamic energy will be converted to what we call or into the shape of what we call the pressure wave. So all thermodynamic energy in the confined explosion will end up as a pressure wave. And the confined explosion can be represented, or the robustness of the explosion can be represented by something called the deflagration index, or it can be used or represented by what we call the cubic law, where the cubic law states that the change in pressure with respect to time at the maximum point multiplied by the volume of the reactor all to the power 1 over 3 equal kg or kst, where k is what we call the deflagration index, and the unit for that is bar meter per second, and G stand for gas and ST stand for dust. And you can find these values for K as if I'm using kg, this means that this is deflagration index for gases. If I'm using KST, this means that this is deflagration index for dust. You can find details about kg and KST in table 6.7 and 6.8 in your book, but again, K is an indication of how robust is your explosion or how strong is your explosion. The higher the value of K, the more strong is your, or the higher, the more robust is your explosion. and it depends normally on or this cubic law depends a lot on experimental condition. That's why, if you still remember, do you remember from where we get this one? This is what we called before as the flammability properties of gases. If you still remember it early in chapter 5, early in chapter 6, when we explained that in order to get, you get two properties, you get, and do you still, I hope you still remember this, where you get the maximum, this is what we call dB over dt max. You still remember the closed reactor, we said that this is like, this is the properties that you can obtain, or this is a function, or this is the material that you are looking for when you are dealing with gases. The flammability limits of gases can be measured inside a closed reactor, and we said that we're gonna mimic what we call the confined explosion, and from the chart of pressure, of the change of pressure with respect to time, you get dB over dt, which is the maximum value of dB over dt, and you get also something called Pmax, which is the maximum pressure. So you see, this is the example, or this is the usage that we for the fundamentals properties that we have learned early in chapter 6. So this is an example of what we call confined explosion. So confined explosion is explosion that takes place inside the reactor, inside the closed system, inside the column, inside the tower, inside the reactor, where I'm gonna, for example, investigate the flammability properties of certain gases, which means that I'm converting all the thermodynamic properties for the system into what we call pressure wave. In this slide and the next two slides, you will see values for what we call, or what we call the flammability properties of gases, where as I mentioned earlier, we are interested in two things. We are interested in Pmax, and we are interested in the deflagration index, Kg, for certain chemical, for acetylene, for example, ammonia, butane. You can find, and this is like the name of the reference, or the name of the work has been done by these names. And you can see that there are, for some chemicals, you can see, for example, for butane, for example, if you are using NFBA 68, you will get 8, and if you are using part inject, you will get also 8, but for Sincel and Peter, there is no values reported. And Kg is what we call the deflagration index, also obtained from these different experiments. So these are the values for Pmax, bar gauge pressure means, and the deflagration index Kg for different, for the list of chemicals. And you don't have to memorize any of these values, it will be given to you if needed. Okay, all you need to know is that Kg stands for the deflagration index, and the unit for that is bar meter per second. And Pmax is another property that we are looking for, or interested to know for, or to understand the flammability behavior of flammability properties of the gases. So this is for, normally this is the deflagration index for gases and vapors. In the next slide we will see for dust. In this slide you see the, what we call the deflagration index, or Kg, or KST, which is the deflagration index for what we call dust. And this is like for certain material, or different material, different type of material. If you have the medium particle size, for example, how much is the medium particle size, how much is the minimum explosive concentration limit, and you get Pmax and you get KST for each material. Because it's very important, if you still remember from the sugar plant that we have discussed in the class, that the particle size is very important, and not all dust are explosive. The dust explosivity or flammability depends a lot on the physical properties of the material, especially the size of that particles. So it's important to know how much is the size of that particles. And you can see that there are certain classes, ST0, ST1, 2, and 3, based on the deflagration index value that you have. But for us to know, you don't need to memorize any of these data or any of these numbers. All you need to know is that the KST is slightly different than the Kg. And the KST in terms of dust explosive, or the deflagration index for dust explosion, based normally on the concentration of the dust and the size of the dust as well, or the particle size of the dust. This is again continuation for table 6.8. These tables are available in your book 6.7, 6.8. This is again another type of dust, and how much is the KST and the Pmax for that specific dust. And I hope you still remember this chart. This is the chart that we have discussed before in terms of gas flammability, when we said that you plot data for gas pressure or the pressure of the gas with respect to time, and you get the curve, you get dB over dt at the maximum condition, and you get also the maximum pressure. These are the two properties that you are looking for, Pmax and the dB over dt at the maximum condition, to get, for example, what we call before as, or using the cubic law, you can calculate, for example, how much is the volume of your reactor, or how much, for example, is the kg of your system, if you don't know how much is the kg, because kg will be equal to v to the power 1 over 3 dB over dt. And from that, if you know how much dB over dt, you can calculate how much is dB, delta V divided by delta T in this case, and you know how much is the volume of your reactor, then you can calculate how much is the deflagration index. And this is again an application for that piece of information or exercise that we have done at the beginning of chapter 6 about how to calculate or how to find the flammability properties of the gases. An example of confined explosion, this could be within a unit or a small reactor, so we can see how much is the damage caused from that. And as we mentioned, when we talk about confined explosion, means that all the energy that I have transferred, all the thermodynamic energy stored in that material transferred into what we call the pressure wave. And the confined explosion, that the explosion took place within a reactor, within a building, within a unit, within a small unit or a small space.